Hello, this is the section 6.6 lesson. For this lesson you will need your z-score table. Now this section is titled Approximating the Binomial Distribution with the Normal Distribution. This section is a little bit theoretical, but there are several reasons I like to cover it. First of all, some of the formulas that we see in next chapter are built on this idea of approximating the binomial distribution with the normal distribution. And second of all, through the study of this topic, we're going to introduce some terminology that's used frequently in the field of statistics and probability. So let's start off with a quick review of the binomial distribution. We introduced this distribution back in section 5, or chapter 5. A binomial distribution is a specific type of discrete distribution that describes a procedure that meets the following requirements. First of all, we have a fixed number of trials. That means we do something over and over again. Number two, the trials must be independent, meaning what happens on one trial has no effect on any other trial. Third is the important one. Each trial has only two events that we commonly call success and failure. And number four is kind of technical. The probability of a success remains the same in all trials. So if we have any sort of procedure that meets these four requirements, we can use this binomial distribution to calculate probabilities. So to illustrate this, let's look at an example. An aircraft seats 120 people, but the airline sells 128 tickets. This is a very common practice. It's called overbooking. And airlines do this because they realize that not everyone who buys a ticket is going to actually show up. Sometimes they just miss the flight. Sometimes they have to change their plans at the last minute. And so their hope is that at least 8 people will not show up, and they'll have enough seats for everybody. Okay. Well, we want to ask, what's the probability more than 120 people will show up? And we want to ask that because if more than 120 people show up, then you don't have enough seats for everybody, and there's a problem. Well, when we calculate this, we're going to assume the probability a passenger shows up is 0.92. So in other words, we're assuming that 92% of people who buy a ticket actually show up. Now this number could have come from aircraft records or airline records. They could look back and see, well, in the past about 92% of our tickets that were sold actually showed up. Or maybe it comes from somewhere else. Okay. So to start off, let's define our random variable we're dealing with here. Call it x. It's the number of ticket holders who show up. That's what we're interested in, the number of ticket holders who actually show up. Let's make a few observations about this random variable. Each ticket holder, or each person, either shows up or not. So we have two events. Showing up, in this case, is a success. Not showing up is a failure. Each of the ticket holders or persons is a trial. So we have 128 trials. And they're independent, or at least we're going to assume that they're independent, meaning one person showing up or not does not have an effect on anybody else showing up or not. Now that's a little arguable as to whether that's true or not, but for the sake of simplicity we're going to assume it's true. So in other words, what we see here is that this random variable meets the requirements for a binomial distribution. So the number of tickets who showed up is described by a binomial distribution with n equals 128, that's the number of trials, and p, the probability of a success, is 0.92. And so back in chapter 5 we talked about how to calculate the mean and standard deviation of a binomial distribution. So the mean mu was n times p, which in this case comes out to be about 117.76, and then sigma, the square root of npq, comes out to be 3.096. Okay. Now remember, in the binomial distribution, the mean mu had a special meaning. It was the expected number of successes out of those n trials. So in this case, a success is a person showing up. So we would expect about 118 people to show up. Now that's good news for the airline, because if only 118 people show up, they're going to have enough seats with 2 left over and everything's going to be fine. Now that doesn't mean that exactly 118 people are going to show up every time. That's just an expected number. Well, before we get to the original question of what's the probability that more than 120 people show up, we're going to ask a simpler question to begin with. What's the probability that exactly 120 people will show up? So in mathematical notation, we want to know what's the probability that x equals 120. Now, we can easily calculate this on our calculator. Remember, when we talked about the binomial distribution, we calculated those probabilities using the binom PDF function in our calculator. And so we could punch this into our calculator. You don't actually have to, because we won't be using the calculator anymore this section. There you type it in, 128 trials, p is 0.92, x in this case is 120, and there we see the exact theoretical probability of 0.108. So there's about a 10.8% chance that exactly 120 people are going to show up. Okay. Well, we're going to use this question, this first question, to illustrate a very important point. That's kind of the whole focus of this this section. In a program called Minitab, which is a statistical analysis software, I simulated this procedure of selling tickets to 128 people and then having them show up, and we recorded the number of people who actually showed up. And I simulated doing this 5,000 times. So 5,000 times we sold 128 tickets, and we recorded the number of people who actually showed up. And what we have here is a histogram of the results. What we see there on the bottom is X, the number of people who showed up. That ranged from a high of 128 down to a low of about 106. And we see there in the middle 118. That's the most frequent number of passengers that showed up. And remember, 118 was our expected value, so that's what we would what we expect to see. You see there 119, 120, 121. Those are also fairly high frequencies. So one observation we want to make here is that notice the shape of that histogram. It kind of has a bell curve shape. Starts low, increases to max, decreases to low again. It's not a perfect bell curve, but it does kind of have that bell curve shape. So that tells us that our data, our number of people who showed up, appears to be normally distributed. Well, that's interesting because the number of people who show up actually have a binomial distribution, but what we see here is that it's approximately normally distributed. And we can see that even better when we draw a bell curve on the top. Here we draw a bell curve with this mean of 117.7 and standard deviation of the 3.076, which we just calculated a bit ago. Notice that bell curve goes right through the tops of most of those rectangles. Not all of them, but most of them. And that again indicates that we have an approximately normal distribution. And so this motivates the whole idea of this section. We're going to use a bell curve, areas underneath a bell curve specifically, to approximate these binomial probabilities. Okay. Well, to illustrate how we're going to do this, let's look at one specific rectangle. Let's look at this rectangle centered at 120. The width of that rectangle is 1. Now that's true because that rectangle has a left endpoint of 119.5 and a right endpoint of 120.5, so the width is 1. The height, if we look over at the scale on the left-hand side, we see the height is about 0.108. So that means the area of that rectangle, is the width times height, is going to be 0.108. Well, now what's significant about that is that number 0.108, well, that's the probability that exactly 120 people will show up. And so what we've illustrated here is that the area of each one of those rectangles equals the probability of that number of people showing up. Or stated another way, the area of a rectangle centered at a number is equal to the probability that x equals that number, or that many people show up. So if we look at like the rectangle centered at 124, the width is 1, the height is about 0.012, so it means the probability that exactly 124 people show up is about 0.012. Now we could do that for any of those rectangles that we see there. Okay, so we just saw that the area of these rectangles corresponds to the probability that a certain number of people show up. So for instance, we saw that the area of that rectangle centered at 120 is equal to the probability that exactly 120 people will show up. Well, let's just look at how this relates to the bell curve. Here in this figure, we have shaded the region underneath the bell curve between 119.5 and 120.5. And what we see there is that the area of that shaded region is approximately equal to the area of that rectangle centered at 120. Okay, so what this illustrates, and saying another way, is that the area of the rectangle is approximately equal to the area under the bell curve between 119.5 and 120.5. So we can use areas underneath this bell curve to approximate binomial probabilities. So if we strip away the histogram and look at just the bell curve, we're dealing with a bell curve here with a mean of 117.76 and a standard deviation of 3.069. That was the mean and standard deviation of our binomial distribution that describes the number of people who show up. The probability that exactly 120 people show up is approximately equal to the area between 119.5 and 120.5. So let's calculate that area underneath that bell curve and compare it to the exact value that we calculated earlier. So we know how to find areas underneath bell curves. We convert the numbers over to z-scores and find the area. So we're going to take that first number, 119.5, convert it to a z-score by subtracting the mean of 117 and divided by the standard deviation of 3, and that gives us a z-score of 0.57. So we go to our z-score table, look at 0.57, and we find the area to the left is 0.7157. Now we're going to convert that other number, 120.5, into a z-score by subtracting the same mean and standard deviation that we just used, and that comes out to be 0.89. And then we look at our z-score table. The area to the left of z equals 0.89 is 0.8133. And so we subtract that large area minus the small area to get the total area, the whole shaded region there. That comes out to be 0.0976. So that's the area underneath the bell curve between 119.5 and 120.5. So our conclusion here, our exact probability that we calculated earlier is 0.108. The approximation that we just calculated is about 0.0976. And that approximation is pretty close to the exact value, so so we conclude that the approximation is indeed reasonable. Okay? So this illustrates the basic idea and the motivation for approximating binomial probabilities with the normal distribution. Now you may be saying to yourself, well, wait a minute, that was a lot more work than just calculating the exact value on my calculator. Why would I want to approximate it? Well, we'll motivate that more here with our next example. But before we do this, we need to introduce some terminology here. We wanted to find the probability that exactly 120 people show up. And we did that by finding the area underneath the bell curve between 119.5 and 120.5. So we subtracted a half and added a half to that number 120. This idea of subtracting and adding a half is generically referred to as a continuity correction. That we call it that because the binomial distribution is a discrete distribution, whereas a normal distribution is continuous. So to go from discrete to continuous, we've got to make a correction. We call that a continuity correction. Okay. Now let's go back to our original question of what's the probability that more than 120 people will show up? Or stated another way in mathematical terms, what's the probability that x is greater than 121, greater than or equal to 121? Okay. And so let's go back and look at our histogram with the bell curve drawn on top of it. So 121 or more people showing up means that 121 people showed up, or 122, or 123, or all the way up to 128. Well, so what we'd have to do to find that exact probability is we'd have to find the area of those 8 rectangles centered at 121, 122, all the way up to 128, and then add them together. Now that's not terribly difficult to do. We could calculate each one of those exact areas on our calculator using the binom PDF function, add them together, It's not a big deal, but that's a lot of work. I don't want to have to do all those. I don't want to have to do 8 individual calculations and add them up. I want to just do it in one big step. So the probability that we want is equal to the total area of those 8 rectangles. Well, instead of calculating all those 8 rectangles and adding them up, let's look at how this relates to the bell curve. Here I've shaded the area underneath the bell curve to the right of 120.5. Now, why did we go to the right of 120.5? Well, because the 120.5 is the left end point of that rectangle that's centered at 121. That was the first rectangle we were interested in. And so the total area of those 8 rectangles is approximately equal to that area, that shaded region under the bell curve to the right of 120.5. So the probability that I want is approximately equal to the area of this shaded region. Okay? And so again, stripping away the histogram, leaving just the bell curve, we want to find the area underneath the bell curve to the right of 120.5. This is the same bell curve we worked with in the first question, same mean of 117, a standard deviation of 3. So to find that area, we convert the number 120.5 to a z-score, comes out to be 0.89. The area to the left is 0.8133, found from the z-score table. So the area to the right is 1 minus that number, or 0.8167. So that right there is an approximation of the probability that 121 or more people will show up. So kind of rounded off, there's approximately a 19% chance that more than 120 people will show up. Now that's not an insignificant chance. That means 19% of the time there's not going to be enough seats. That's a major headache for the passengers as well as the airline. Okay, so there's the answer to our original question. Now question 3 is going to be a variation of this. What's the probability that 120 or fewer people will show up? Stated another way, what the probability that x is less than or equal to 120. Now there's several ways we could calculate this. We could use complements or other things. The way we're going to do it here is not the easiest, but we're going to use it to illustrate a bigger point. So let's look back at our histogram. 120 or fewer people means that 120 show up, or 119, or 118, or so on and so forth. Well, in terms of these rectangles, that's the area of all those rectangles from 120 to 119 to 118 all the way down to 0. So the probability that x is less than or equal to 120 is the total area of those 121 rectangles. So in order to calculate this exact probability, I'd have to find the area of all 121 of those rectangles, add them up, and find that exact area. Well, that's a lot of work. I don't want to have to do all 121 of those. And so instead we're going to approximate it using this normal distribution. So make an observation here. Here we've shaded the area to the left of 120.5. Now why did we shade to the left of 120.5? Well, because 120.5 is the right endpoint of that rectangle that's centered at 120. So what we see is that that shaded region, the area of that shaded region, is approximately equal to the area, total area of those 121 rectangles. So the probability that x is less than or equal to 120 is approximately equal to the area under the bell curve to the left of 120.5. So we can find that area very easily. It's the same bell curve we've been dealing with before, mean of 117, standard deviation of 3. We convert that number 120.5 to a z-score. Comes out to be 0.89. Find the area to the left is 0.8133. And so there's our answer. There's about an 81% chance that 120 or fewer people will show up. So there's about an 81% chance that there's going to be enough seats, and about a 19% chance that there's not going to be enough seats. So these last two questions illustrated the usefulness of approximating binomial distribution with a normal distribution. Doing the approximation does not require us to calculate 121 different probabilities and add them together. We do one simple calculation, look up the area from the z-score table, and we're all done. So what we've been illustrating in this section is a theorem that looks like this. Says if NP is greater than or equal to 5 and NQ are greater than or equal to 5, then binomial probabilities can be approximated using a normal distribution with mu equal to NP, mean of NP, and standard deviation sigma equal to the square root of NPQ. And now this theorem has these two qualifiers at the beginning. NP has to be greater than or equal to 5 and NQ greater than or equal to 5. These qualifiers, as we've mentioned before, every one of our formulas has some requirements that have to be met. We stressed before, you can't just blindly plug any set of numbers into any formula and expect to get valid results. There have to be some requirements that are met. If those requirements aren't met, you will get an answer, but it's not going to be valid. In this case, we have to have NP greater than 5 and NQ greater than 5. Now let's illustrate what will happen if NP is less than 5 or NQ is less than 5. Let's take the same scenario of we sell 128 tickets and people show up according to a binomial distribution. But let's suppose that P, the probability that a person shows up, is 0.995. So in this case, we're supposing that 99.5% of people who buy a ticket actually show up. And so that means that Q is 0.005. So here I simulated doing this 5,000 times each time we recorded the number of people who actually showed up, and we get this histogram. And so we see here is that we got a bar, really tall bar at 128, a shorter one at 127, 126, 125, and basically nothing to the left of that. So that means that we always have between 128 and 124 people show up. But look at that shape there. It's not at all a bell curve shape. Here we drew a bell curve on top of it. Notice that it just doesn't match that shape well at all. So we see here is that the distribution is not at all normal, nowhere close to being normal. Well, in this case, NP is 127, but NQ is only 0.64. So NQ is much less than 5, and so this illustrates what happens if NQ or NP is less than 5. We don't get a good approximation with the normal distribution. So one last thing we need to kind of summarize here is this idea of the continuity correction. Remember, this idea came from the fact that binomial is discrete, whereas a normal distribution is continuous. And to use one to get the other, you have to do this correction. So in the first question, we calculated the probability that x is equal to 120. We did that by finding the area underneath the bell curve between 119.5 and 120.5. So we subtracted a half, added a half, found the area in between those two numbers. In the second question, we calculated the probability that x was less than or equal to 120. We did that by adding a half and then finding the area to the left, and that was our approximate area. In the last one there, we found the probability that x is greater than or equal to 121, and to do that we subtracted a half and then found the area to the right of that number. Now those last two cases seem a little backwards. Seems like if you find the probability that x is less than some number, you should subtract a half. And if you want to find the probability that x is greater than or equal to some number, you should add a half, but that's not the way it works. You subtract a half, you add a half in the first case, you subtract a half in the second case. And in all these cases, the bell curve has a mean of NP and a standard deviation of NPQ. So you'll be using all these different types of continuity corrections to calculate solve the problems in the homework. So that's it for this lesson. The section is titled, the homework is titled Section 6.7.